Bismillahirrahmanirrahim. In our today's video, we will discuss about state space representation. We apply the state space formulation to the representation of more complicated physical systems. The first step in representing a system is to select the state vector. It must be chosen according to the following considerations. The first is that a minimum number of state variables must be selected as components of the state vector. The minimum number of state variable is sufficient to describe completely the state of the system. And the second is the component of state vector, that is the minimum number of state variable must be linearly independent. So let's review and clarify these statements. So first we will discuss linear independence. If x3 can be expressed in terms of x1 and x2, in this case x3 is not linearly independent of x1 and x2 because x3 is dependent on these two terms. Variables and their successive derivatives are linearly independent. For example, if the voltage across an inductor is V sub L, then the current through the inductor is I sub L. Both will be linearly independent because VL will be equal to L di by dt. VL cannot be evaluated as a linear combination of current IL. So we cannot evaluate these two terms. So given the, let's take an example. In this circuit we have an electrical network. We have to find the state space representation if the output is current through the resistor, that is IR. So let's start the solution. First of all, we will label all the currents. There are three currents: current through inductor, that is IL, current through resistance, that is IR, and current through capacitor, IC of t. Write the derivative equations for all the energy storage elements. So there will be two equations. Current through capacitor is represented with C dV over dt, and voltage is equal to L and derivative of current through the inductor, L di by dt. So we will choose the state variable as the quantities that are differentiated. So we have chosen these two as our state variables. The right hand side of these equations should be linear combination of the state variables and the input, like this. In this case, this is linear combination of input and the state variables. We will now apply the network theory to obtain IC and VL in terms of state variable VC and IL and the input V of t. This is our equation of current through the capacitor and voltage across the inductor. At node 1, IL will be equal to IR plus IC. So here we get IC equal to minus IR plus IL, because IL is sum of IC plus IR. So entering the value of IR, because this is equal to VC over R. So writing loop equation for the outward loop, we'll get input will be equal to voltage across this inductor plus voltage across this capacitor. So here we have C dV over dt is equal to IC, and we have get the value of IC equal to this term. We will place this term in this equation. Similarly, VL value is obtained from here. Current is obtained from KCL, and VL is obtained from KVL. And take these two terms in this equation, we get these state equations. These are first order equation. Dividing with this equation with C and the second one with the L, we get the state equations like this. From here we can write in the matrix form, and the output is in the we require IR, which will be equal to VC over R. So here this is derivative of VC and IL. This is our X derivative matrix. The A matrix will be equal to coefficients minus 1 over RC, 1 over C, minus 1 over L, and because IL term is missing here, so it will be equal to 0 like this. Similarly, state vector here, and B matrix is here no input, so this will be equal to 0. Here we have 1 over L coefficient, so 1 over L will be written here. IR, the output matrix, will be written in this form. Because IL equal to 0 in this case, so 0 will be written here. So this example clarifies the linear independence topic. For minimum number of state variables, the minimum number required are equal to the order of the differential equation describing the system. For example, if a third order differential equation describes a system, then there will be three simultaneously first order differential equations are required along with the three state variables. From the perspective of the transfer function, the order of differential equation is the order of denominator of the transfer function after cancelling common factors in the numerator and denominator. So this concludes our today's topic of state variables. Thank you.